Okay, thank you everyone for coming to today's workshop. The workshop is Beyond mAP, Reassessing the Evaluation of Object Detectors, or BMREOD for an attempt at shortening. Before we get too deep in, I would like to thank very much the other organizers of the workshop, so Niko, Faras, Gustavo, and Chunwa, for helping make this workshop possible. They were very instrumental in the proposal for this and very helpful all the way along in creating this workshop. So big thank you to all of them. The workshop, if I could sum it up in a sentence, is the concept that quantitative results should be easily reconciled with the detector's performance in applied tasks. If you're going to use an object detector for something, then you should have numbers that evaluate how good it is, and they should make sense with what you're trying to apply the detector to. The goals of the workshop were to identify gaps that might exist in our standard evaluation procedures for object detection, to try and promote alternative approaches to evaluation that try and address these gaps, things that enable an increased insight into how our detectors are working, and that better equip us to start applying object detection to real-world problems with some degree of confidence. This is also the platform where we hosted the third probabilistic object detection challenge, which promoted object detection with meaningful spatial and semantic uncertainty output for robotics applications. In total, we had 12 video presentations that I recommend people check out, with 3 invited speakers, 2 self-indulgent organizer talks, 4 workshop papers, and 3 probabilistic object detection challenge papers. So thank you to everyone who has contributed, and I definitely recommend people check things out. With respect to the probabilistic object detection challenge, I'd like to quickly thank the Robotic Vision Challenge team who worked on probabilistic object detection, team members both past and present. Thank you very much for making the challenge what it was able to be. We do not have any of the prod challenge participants in this individual interactive session, but there will be a recording of the previous session available online, and you can go check that out to talk to other participants of the prod challenge. Overall, I would say to everyone, please enjoy the workshop session. Ask as many questions as you can to the panel in the Q&A. This is very much supposed to be an interactive session, which is only interactive if you actually talk to us. Please ask as many questions as you wish, and we'll try to get to them. I would recommend you watch all of the workshop videos and read the workshop papers. There's some very interesting insights into evaluation methods for object detection and the new field of probabilistic object detection. And yeah, generally just enjoy yourselves. If you have any questions about robotic vision challenges, etc., here's a bunch of contact details we have on there. So that is the end of the sort of formal presentation part. Now happy to open things up to the panel, and I'll ask you all to introduce yourselves and tell us a bit about what you do. I'll go through this in the same order that we had on the workshop website. So Emre, would you like to introduce yourself?
Sure, thank you, David. Thank you for the opening. My name is Emre Akbas. I'm an assistant professor at the Department of Computer Engineering, Middle East Technical University. For those of you who don't know where Middle East Technical University is, in Ankara, Turkey. I received my PhD from University of Illinois at Urbana-Champaign, and then after that, I worked at the University of California, Santa Barbara Department of Brain Sciences as a postdoc researcher. And then after that, I joined my the department where I graduated from, Middle East Technical University. I work on object detection mostly, and human pose estimation, and machine learning, deep learning, and computer vision in general.
Cool. Thank you, Emre. Jonah, sorry, not Jonah, Marco. Marco's next. Marco, would you like to introduce yourself?
Yeah. Good morning, good night, good evening. So I'm Marco Manfredi. I work at TomTom in Amsterdam, the Netherlands. And I've received my PhD in Italy in 2015 at the University of Modena and Reggio Emilia, working in segmentation and object recognition. And yeah, TomTom, we do HD mapping, so the maps for autonomous vehicles. And there I'm focusing on object detection of road markings and like arrows, text, and other stuff on the road. So I'm very actively looking for the research and new ways to evaluate object detection. So that's why this workshop is very interesting for us. And yeah, that's it.
Cool. Thanks, Marco. Right, Jonah, how would you like to introduce yourself?
Sure. Yeah, so I'm Jonah. I just started my second year of PhD at University of Toronto with Sanya Fiddler. And I'm also a research scientist at NVIDIA, also under Sanya. And I'm from Chicago, and that's where I currently am, where it's 2 a.m. And I studied physics and math in undergrad. Yeah, and I'm excited to be on this panel, hear what you guys are thinking about around this topic, for sure.
Cool. Thanks a lot, Jonah. Then the only two remaining panelists are myself and Niko. So we are both postdocs at the Queensland University of Technology, working within the Australian Centre for Robotic Vision and the QUT Centre for Robotics. Specifically, we are part of a Robotic Vision Challenge group, which is a group that is dedicated to creating robotic vision challenges to allow us to reliably evaluate and compare robotic vision systems that can be hopefully applied to real-world scenarios more easily. All right, now that we are all introduced, I will start with the first general overarching question, which I'll throw open to everyone, but we may start with Emre's thoughts on this, which is, what do you think are the blind spots that we potentially have within evaluating object detectors at present, given the current paradigm of detector applied on a data set, get mAP out?
Okay. That's a very good question. Thank you. So AP, as we all know, is the golden standard right now. Everybody uses it to evaluate not only object detectors, but also segmentation methods and other stuff. But there are certain weaknesses, there are limitations to AP, which we addressed in our talk, but let me remind of those limitations. First of all, AP does not consider localization explicitly. So if your intersection of union, intersection over union is larger than a certain threshold, then you're good. And it doesn't care about how good your localization is. With COCO style AP, you can sort of remedy this problem, but still, whatever threshold you use, you still have this problem. And then the next thing is, it doesn't consider false negatives explicitly. That means if you missed some of the ground truth boxes, it is only implicitly included in the area under the curve calculation, because you don't have any precision over some area of the recall line, and then that lowers your area under the curve. But AP is not able to distinguish between different error cases. If you have low AP, you don't know whether it's because of your low recall or low precision or something else. So I would say these are the three major limitations or weaknesses of AP. And in David's talk, there was a very nice example, obscuring false positives. So if you have lots of false positives with low confidence scores, it won't affect your AP. It won't change your AP, but in a robotic vision, in a real world application, it's certainly a bad thing.
Cool. Thanks, Emre, and thanks for the shout out as well. Would any other panelists like to chime in here with their thoughts?
Yeah, I think so. If you have to start working on object detection, maybe use the Coco evaluation API, and you just get AP out, and then you immediately understand that in a real world application, that number is not enough. And what I find myself doing most often is looking at the PR curve itself, and because in a real world application, you want a nice working point for your application. Like the AP is this, like, that's the end area under the precision record curve, basically, and this doesn't tell how good this detector is on your application. Maybe you want very high recall and just a decent precision of like 80% or whatever, or the other way around, you want to be very precise. And yeah, so then in the end, a method that has a better AP, it's not 100% the method that will have the best working point for you, for your application. And the second thing is that that evaluation procedure doesn't promote outputting the correct number of predictions out. So it's the AP usually is computed with outputting 100 boxes per image, even if that image doesn't have any ground truth. And it's kind of related to the issue you talk about for the false positives that Emma just mentioned. The false positives sometimes are not penalized, and I think a good detector should output the number of objects that are in the image, not like always 100 boxes and then hopefully there you do have your true positives. So I think that should be promoted and evaluated differently.
Cool. Jonah, did you have anything you'd want to add to that?
Yeah, actually, so one other thing I wanted to mention is that like AP is also kind of a global metric in the sense that you need a lot of images to get a curve which is going to give you a reasonable value of AP. You can't just like take a mean of AP across several images. I think like ideally we would be able to optimize for just like precision or whatever metric we wanted to evaluate with. And this fact that it's not like per image makes that a little bit harder. And there are a lot of really cool papers that are trying to do that. But I think that's a challenge. And one other thing I wanted to mention is that like in my workshop paper, I'm talking about object detection as it relates to self-driving. And in self-driving, like what I think Marco said this, like it's really the downstream task that matters. Perception is not the end goal. Like the end goal is driving the car in a safe way and getting people from A to B. So the way that like that downstream task interacts with perception performance is like really complicated. But that's the thing that you really want to take into account. So the detector that gets the highest AP is not necessarily the one you want to put in the car. There are also like some other papers at ECCV this year that were trying to figure out ways to make metrics for perception correlate more strongly with like the downstream task that you ultimately care about.
It's actually a very interesting thought to try to measure the performance with respect to some downstream task. Maybe can we expand a little bit on this and talk about where does this, what are the limitations of this approach? What are the downsides? It sounds very, very appealing, but are there any downsides to it?
Yeah. So one thing that I've come across with is, so object detection usually requires like a non-maximum suppression, right? At the end of it. And we do have techniques like soft NMS, which allow you to differentiate through that. But if you want to measure a downstream task and optimize for it, then it's just tricky to deal with like that clustering in the middle. If you just want to evaluate, then then you also need some sort of like simulator, maybe for driving at least. You need some sort of simulator so that you can actually take actions and measure quantities like how long it's taking you to get from A to B and how many collisions are happening per second. Hopefully it's a very low number. Yeah, but I'm also curious, like what applications you guys have in mind for when you're talking about object detection, like for TomTom, like for building maps, like you want to detect like lanes, right?
Yeah.
So it's gonna be very, yeah.
Yeah, for example, we detect, let's say a very simple case of arrows, like that every junction you have multiple arrows, just want to automatically detect all of them. But that in the end, the product that TomTom sells is a map that has to be 100% accurate. So we do have humans down the line that check what the detector has done. And so if you think, okay, let's just try to, what we want is actually to optimize the time from detector to perfect map. And that's going to be tricky during the optimization process, right? Because you do need a human that fix the output of a detector to make it perfect if necessary, and then try to measure the effort in doing so in terms of time, clicks, or I don't know, just number of adjustments in the bounding boxes. So we do have these metrics, of course, but we didn't really figure out, and I don't know if you actually can figure out the effort to fix them. We try to actually we are actively investigating this on now really to find a metric that is better than mAP for our case, that tries to say, yeah, a false positive has this weight in terms of time, like throwing a new box as a certain weight, removing a box as a certain weight, and trying to measure the effort that annotators take to correct these errors, and try then to integrate and try to rank our detectors based on that. So that's like an attempt on going to this direction.
I'd say one thing that was brought up in like the previous interactive session was the idea that whilst it'd be good for us to have this this ability to sort of branch out and go, all right, specific evaluation procedures, etc., for specific downstream tasks, what is it being used for? It still is going to need to be complementary to just the general task of object detection. So in the previous panel, it was being argued that, well, we're not good enough yet at just base object detection to be able to just completely ignore the generalized task, and also that we should make sure that any sort of methodology we use can be sort of cross-disciplinary and cross tasks. And I see, particularly from Marco and Jonah, you're both very applied, very set situation. Do you also agree that there's still a place for that sort of more generalized look, or do you think it should all be very sort of specialized?
If the community would have specialized in all these different branches and all these different applications, we wouldn't have COCO, right? The COCO challenge and just the ability to rank objects based on a common metric. So yeah, as a community in academia, we need one way, or at least we need one way to measure detectors, and for now AP is what we have. But for now we are really stressing when you move away and you just want to apply this to something, either robotics, autonomous driving, or for us mapping, then you do have to step away from that mAP. So yeah, we do need a common metric. Yes, we cannot. I don't think we can just specialize and be just unable to compare to each other just because we are looking at our small applications.
Can I maybe add a few?
Of course, yeah.
Definitely.
Okay. I certainly agree that evaluating object detectors with a downstream task makes a lot of sense. That's definitely, we should know it. But I also agree with David that the base object detection is still not there yet for real world applications. So take COCO, for example. We are at what, 0.5, 0.55 MAPs. And then there's also the problem of long tail recognition. So COCO is much more realistic than Pascal, than the previous object detection dataset, but still it's not the real world, and we are not even very good at COCO yet. So I think that kind of optimizing the evaluation metric, trying to maximize the performance there is still relevant. So both are relevant.
This morning we discussed a little bit that the performance on COCO is sort of saturating, so, or even not going up anymore, and then it was basically Larry Zitnik who sort of suggested that it's might be time to retire the data set and go to a more difficult one, because we don't see much progress anymore. And it was kind of interesting to talk about how data sets and evaluation metrics really push the field in a certain direction, and help sort of shine light in that dark corner where we're not making or not doing much research because it's hard to evaluate that. So maybe I want to repeat the question that we had earlier in the other panel today. If you think about what kind of problems do you think are very important for applications of computer vision, but we don't really have a good metric to evaluate them, and therefore there's not much happening in terms of research in that area. So what do you think are these hidden dark pockets where we should shine light in the form of new evaluation metrics and data sets to make progress in?
So should I go first? Okay.
Go for it.
I think in terms of application, autonomous vehicles might be the most important, and it might be the application that will have the highest impact in the near future, probably. But in the data set and evaluation side, I think there are a lot of room for improvement. As I said, the long tail recognition problem. So you have, there are a few classes with a very large number of examples, and there are a lot of classes with very few examples. And this is not really incorporated into object detection yet. COCO, of course, the number of objects per class is also varying. That's good. It has some sort of long tail distribution, but real world is much more significant, real world classes. Maybe we should move on to data sets like Elvis, and then, for example, the iNaturalist data set, a good example for the long tail recognition. And I think we need more data sets like this in the object detection too. And in the evaluation metric part, I think we should look for better metrics. As we said at the beginning, AP has certain limitations, weaknesses, and people are trying to address them. One effort I know is probabilistic detection quality. It takes into account the label uncertainty and the spatial uncertainty, which are very important, and they are not taken into account by the classical measures. And also localization recall precision, our work, which looks at the problem in a unified manner. It looks at the localization and classification at the same time. And I think it will certainly provide more insight into your object detector than just the single number given by AP.
On that note, Emre, when designing PDQ, and partway through, we'd also read your LRP paper. it became very clear that the ability to break up a measure into subcomponents to analyze these specific bits about how does it work was very important. But at the same time, we've, as a community, we've sort of gotten a bit into focusing on that one summary statistic. So for PDQ, that'd be the overall PDQ score. And even though, yes, it's useful and it incorporates all these bits, it's still not that full distribution. And I'd say I'd possibly I'll post the same question as I had in the previous session of, do you reckon that it's on the onus of the people who are developing object detectors to try and make sure that in their analysis, when they're proposing a detector, they go to this nice in-depth analysis of all the different subcomponents about exactly how their evaluator works, whether it's good with all classes, whether it's good at all aspects of object detection, or as a community, should we possibly start just being more accepting and more willing to create just pure analysis papers that take whatever the state of the art is and dissect it into all of its component bits?
I think going into depth of analysis would be certainly useful, and we can create tools for take any object detector and any data set that should give us component-wise analysis, because it will provide more insight on where the weaknesses are, how it can be improved, and yeah, I certainly agree that there should be we should have tools that makes this analysis for us, because it can be automated, I think. And then every paper, every work can use it, and it will be easy to put this in-depth analysis into any object detector.
Cool. Definitely preaching to the choir here, but definitely agree. How about Jonah and Marco? Do you have any opinions? Are you more on the analysis side or on creating own object detectors and analyzing, thoroughly as you go?
Yeah, I was going to say, like, I think one of the number one benefits of having good evaluation metrics is that it tells you where to focus your time and like what to prioritize, and where you can improve, like make big improvements. And part of that is writing down good metrics, and another part of it is like developing good upper bounds on what you expect that metric to eventually achieve. Like for Cocoa, I was actually going to ask if anyone knows if there's a human benchmark, like on ImageNet, like Carpathy got like 91% or something, top 5 accuracy, I think. I was wondering if anyone knows if there's a Cocoa upper bound.
Not that I know of.
Yeah, I don't know of any.
I think Larry this morning said, right, that we can't expect to get to 100% because the labeling is noisy. There are mistakes in there, and apparently they went through. He talked a little bit about the experience of building the data set and how long they iterated over. How is it annotated, and how different people can't even agree on how to annotate it in a certain way. So there's like really a big, some gap to 100% just because of how we label these things.
Yeah, so I think getting that upper bound, getting the good metric, getting a good sense of the lower bound and upper bound, I think that can really help in like figuring out where current methods are failing, and where to focus the efforts. Yeah, and actually that I just want to mention one more thing, which is that was kind of one thought behind our workshop paper, was there are all these 3D object detection metrics on like Kitty or New Scenes, Lyft, Waymo, Argo, that a lot of companies have come out with these new data sets. And on every 3D detection leaderboard, the LiDAR-based detectors are always performing like significantly better than image-based 3D detectors. And we know that like we can drive with just stereo vision, and probably even monovision. So like one of our questions was like, well, can we find a metric where like LiDAR-based and camera-based 3D detectors are performing like more similarly? Because maybe LiDAR-based models can detect better, like for vehicles that are like very far away or like that are parked or something. But those cars actually don't matter that much for the driving task. So yeah, I think evaluation is good when it can tell you like where things need improvement. Yeah.
Yeah. Sorry.
Yeah, just to go on the evaluation, something that also we strive for, like in our task, is that we want to get the highest number of boxes right, whatever the class. So in the end, AP that averages out the imbalances between classes in the end, right? Because it's just weighted across classes. If you have 5 classes and one composes 90% of your data set, that one class will still count 1/5 of the total AP. But that's not, at least for us, for our downstream task, that's not how in the end you would measure success and value. So the first thing we did was like kind of a weighted AP, where each class is weighted by the number of instances of that class, because then that goes a bit like in the opposite direction of Elvis, right? Because in some tasks, like maybe autonomous driving, you want the corner cases to be as good as the frequent cases, because the corner cases or the rare cases are the ones where people get killed or people get hurt, and you don't want that. But for our case, if we have some, for example, we are analyzing the entire US right now, and you get signs that are always or only in Sacramento. Who knows why, but just that municipality found out very weird sign that is, we found the other day, and just so rare that, I mean, why should I care? I shouldn't drive my detector to find this rare category, but and maybe inexpensive, like by losing some performance on very frequent classes, like the straight arrow. The straight arrow is everywhere, and I want to get it 100% of the times. So that's just a different way of seeing the imbalance problem, just by saying, yeah, if the world is in balance, the frequent classes are the one I want to get right the most, because are the one that's gonna have a bigger impact in the end. And the second thing about what we are missing, I think about in evaluating detectors, kind of relates to both autonomous driving and our paper on shift invariance, that I think it might be good to have an evaluation or a data set that tries to measure the consistency of a moving object. It's like consistency in detecting a moving object, so that we can see, I don't want to miss that pedestrian crossing the street in no frames, even if I have tracking possible, but I want the detector to be as accurate as possible in every possible frame. So like the consistency on moving objects, I think it's missing.
We have one question from the audience. You probably all can see it, but I'll read it out. There's big concern on the labeling noise of the existing datasets. For example, after a long time research on the cityscape semantic segmentation benchmark, we find there exist many annotation errors that cannot be ignored, such as misannotated persons, inconsistent annotations for some less well-defined concepts. I'm wondering why the owners of all these datasets do not spend efforts to improve their annotations. If we cannot remove the noise as much as possible, then we might keep trying to overfit the meaningless noise biased error patterns. So what do people think of that one? Can we remove all error in our data sets to make for better object detection, evaluation, and such? Is it a physical possibility?
I think our detectors are good enough to spot some of these errors. I think if you take even the training set of cityscapes and you run inference of your detector, and just sort the errors by confidence, I think you would find errors in that way. That's what we are doing also on our data. Like ground truth labels large scale are never perfect. Yeah, because of some situations, as the questions also states, are ambiguous or not well defined. And sometimes I think our own method are able to find to correct these answers. So just by really running the detector on top of it might be a quick way to fix some of the big errors. But then you change the data set, so then you have to, all the literature before that change and after that change then needs to be compared differently. And I think this is the why they don't do that.
I guess
you know,
go, Niko.
Yeah, just maybe want to remark that I guess whatever we do, I don't think any data set will ever be perfect if it's a large scale data set and if there's human annotation involved, right? Which there has to be. So I think people and the research groups who put these big data sets out there, I think they invest a lot of time and money and efforts into them, which is great. And I think we just have to accept that they won't be 100% perfect, and that whatever methods we train have to be robust to that, or we just have to be aware of that this is what it is. So I don't think it's about that the people who put these data sets out there are not willing to put the effort in. They already have put the effort in, but it's just not possible.
I'd add to that even when using simulation to create data sets, such as we've done for some of our challenges, the only way that you're getting a consistent label from that is by the fact that there's usually only one or two people deciding what every 3D model should be labeled as. And even then there can be ambiguity. I remember in our new scene understanding challenge, there was a discussion at one point as to whether or not a perfume bottle should be counted as a bottle, because it wasn't, the classic sort of wine bottle type thing or water bottle. And so there are those sort of ambiguities in data set creation, even if you're using simulated data, which not everyone is comfortable with using for testing real world systems. So yeah, it's definitely not an easy question to answer.
And I think for that reason, right, that's why we need probabilistic evaluation metrics, right? Because the point is that it is a distribution of possible labels with non-zero variance. Yeah, you just can't expect if you train a model to be deterministic or be unimodal, it's gonna be more prone to errors due to problems with the data like that, I think.
Yeah, I think it's an important problem, and I agree with the comments that our data sets will not be 100% clean. So we have to account for this label noise, and there's this problem of few classes or few examples per class. I think the machine learning community who are working on imbalance problems are ahead of us in this sense. For example, there are works on imbalance and uncertainty, where the low number of examples per class and label noise are considered at the same time, and it's showing great performance on this imbalanced data sets. There's actually a great talk in the IPCV workshop, Tengyu Ma's talk, which is exactly on this topic, and I think we should borrow those techniques, those paradigm there to object detection. That's very important.
Thanks. We have another question from the audience, so from you. The question is, one important aspect of machine learning algorithms is the robustness analysis. Would you be in favor of integrating robustness into the, quote, standard evaluation? Answering for myself, I would definitely say yes. So again, in the first interactive session, we had Walter Schreier coming and talking about just that issue of basically evaluating robustness by introducing a gradually increasing amount of noise of some sort, error, changing rotations, all that sort of stuff. to be able to get a better understanding as to how an object detector will break. Just keeping on tuning the dials until things break and establish what things are good and bad against. From my own experience, my first paper was a paper on leaf classification, and in that one I was just testing out whether or not deep learning could actually classify leaves. They can, but the big shock, I know, but the big thing that I enjoyed doing that paper was just that you tweak the dials, you rotate the leaves, you make the leaves darker, lighter, you take chunks out of the leaves to see whether or not all the various classification methods could still evaluate them. And it was really gave me a lot of insight, and it was very interesting and useful, I think, to be able to have that extra information. So definitely, particularly if as a community we are more accepting of deep analysis papers as opposed to just I did the data set, I got a good number, give me a paper, then I think that's definitely something worthwhile exploring.
So there's a lot of papers out now, I think, on ImageNet C and ImageNet, I was called A. So ImageNet C, I think it's the ImageNet with 15 kind of corruptions, noise and rotations. Then ImageNet A, I think it's on adversarial samples. So maybe, yeah, the detection community might need a standard way of doing this or evaluating this. That might be worth the effort to have a data set to measure this. Although I would say that I think ImageNet C doesn't, I don't know if it contains the translations, because yeah, we found out translations are also like the kind of robustness you might want, but maybe it's not the usual corruption you think when you think of yeah, corrupting an image, just shifting it 1 or 2 pixels.
On that,
yeah.
Jonah, you go.
Oh, okay. Yeah. I just wanted to say, well, I think I do have somewhat of like an opposite opinion. In that, like I feel like it again kind of has to do with like the task that you're ultimately going to use your detector for. Like for instance, Alex Madry has been building lots of these adversarially robust loss functions, right, which encourage models to be less sensitive to like L0 or any norm perturbations. And they had a very difficult time getting those models trained with those losses to actually perform better on like the, an ImageNet validation set under like top 5 or top 10 accuracy. Obviously, when they test according to their loss function that they use during training, then they're performing better than standard CNNs. So I think it's really tricky. Like I'm not like, sometimes perturbations to the input are not like, even if your model responds to them in a unusual way, it doesn't matter that much. Like if we change, like Novak Djokovic is like the best tennis player in the world, right? And like if you change the tennis court size, like he might not be the best player anymore. But that actually does, like we don't actually care about that robustness that much. Yeah, so I guess that's my thought about that. Or with leaves, like rotation and variance, I could see being more important for like a leaf detector than like an arrow detector, like where like you actually want it to kind of shift, be equivariant with. Maybe that's not a great example, but I think I got the point across. Yeah.
Yeah, no, and it's good to have the conversation and have someone with an alternative opinion. My general frame of reference has always just been that if a human would not be absolutely flabbergasted by a change, then we can't claim a good object detector unless it's able to cope with that same sort of change. So that's my general thinking on it.
And so we go a bit back to the like task specific robustness or the general metric to measure it, right? So I completely agree that probably that ImageNet C tries like 15 perturbations, but in your task or in autonomous driving, maybe you care about 2 or 3 of them. But then you do not want, again, I think, to just split this robustness investigation in so many directions that then every paper is okay because it just measures different kind of robustness, and it can be a bit very hard, I think, to compare in the end. So yeah, it's a bit of a trade-off between how general you are and how can you compare with everybody else, and how you are actually care for your task at hand.
On a related note, I think, another question from the audience from Jen. Have you thought about how to protect the physical adversarial attack to the object detection? So I'm guessing how to protect from adversarial attacks to an object detection system. Anyone have any thoughts on that? I do not.
This is a question for autonomous driving, Jonah. I don't care about that, I think, usually. Autonomous driving might be.
So this is like, for example, like putting a sticker on a stop sign, which makes the car think it's like a green light.
So,
yeah. Okay. Yeah, I think so. The approach that I've seen people do on the AV team, like most often, right, is like data augmentation. So if you can like simulate your environment and be able to like add in things like stickers or lots of noise, as much noise as possible, then like the models become slightly more resilient to that. But I also think that like these models are all very high dimensional, and you're usually going to be able to find some way to make them do something that you didn't train them to do. So you need like system checks, basically, like models that maybe aren't accurate, but they perform some other functionality that is reliable in some sense, so that you can like maybe depend like you need some way to basically to know when your system is uncertain, and that goes back to like probabilistic detectors, and also yeah, just having these other checks that your system runs. Yeah, but it's definitely a difficult thing to think about, and definitely important.
I'm often wondering, both the probabilistic aspects and also robustness to these adversarial attacks, and also robustness to open set conditions, are all a bit connected, because we are doing a lot of, at the end of the day, it's just some linear classification after we've done all these nonlinear mappings into a space where we can linearly separate things, or separate the classes. And we're not taking distance to the training data set into account. So I'm often wondering whether these distance-based or metric learning-based methods would be more robust, basically just inherently more robust to adversarial attacks and open set objects. So I think that's still an interesting direction for research. I don't have any definitive answer.
We have another question from the audience, all about the mAP metric. So they're wondering how much the mAP metric is sensitive to confidence score. For example, in the paper Panoptic Deep Lab, a simple, strong, and fast baseline for bottom-up panoptic segmentation by Chang et al. By simply changing the definition of confidence score in table 11, AP value is increased approximately 6%. AP and confidence. Emre, would you like to take a crack at this one first?
Okay. I don't know of this specific paper, but I think this is a known issue. AP is not sensitive to the confidence score. What matters is the ranking of your detections. When you have just a single class, it's not a problem, probably. But when you have multiple classes, then, I mean, still ranking is important, but if you are squishing the scores for one class into a narrow range and for some other class into a broader range, and then those confuse your detector, right? And then AP is not able to cope with this score, so it's not score sensitive. This is also addressed in David's talk. There was a nice example there. So I think this is a non-issue. Yes, it's not sensitive to scores.
Yeah, like for me, the biggest frustration has been the fact that label doesn't mean anything in actual sense. So like when creating PDQ, it was very important to us to like have the label score actually mean something. And PDQ definitely doesn't have the perfect solution. It's not looking at label calibration, which is another very important issue within creating object detectors that are reliable. But it still means that the label score will mean something. So yeah, very much, I would not be surprised at all if someone was able to tweak their AP scores just by changing confidence values, because all that matters is ranking.
Yeah, I think the with mAP, also what we found in our paper on shifting variance, the very like hard thing to predict is how the change of a confidence score of a certain prediction might affect the overall AP, because you think, oh yeah, I found this cow in this image of Coco, and the score goes from 63 to 60 if I just move that image a little, and you see, okay, all the false positive are lower than this 60 or 63, so you think this small change in confidence might not really have an impact, because you just you still have found that cow, right? You're happy with that, but then when you rank with all the other 5,000 validation images of Coco, that 3% actually changes the ranking of your true positive, and even if it's a small change, you would end up having a different AP. So I had a look at the paper. They say, yeah, if you take the objectness score of a box or the class score separately, let's say in a faster CNN way, you just have the class agnostic score or the class specific score. Maybe you multiply these two, and they do the experiments, and they see, yeah, you can go from, like the AP can change several points between these. So yeah, just hands-on experience that yes, just a small score change that you might think is not that relevant affects ranking. Where you have hundreds of thousands or tens of thousands of predictions, it always affects ranking, even a very small difference.
We have another question from the audience. Really interesting thing happens in the COCO challenge of ECCV 2020. All the results from top 1 submission on phenoptic segmentation - object detection human pose are worse than the top 1 results of the previous COCO challenge of ICCV 2019. What do you think about this problem? Is it mainly caused by the design of the evaluation metrics? If so, can we expect to keep improving the results measured by the new metrics year after year? If not, what are the most likely reasons?
So maybe I can go ahead with this. Okay. This is an interesting thing. I can think of 2 reasons. The first one could be, so people are optimizing a loss function, right? And I believe they optimized it better compared to the previous year. So this might just be a classical case of overfitting, maybe, because I assume that this year the participants to the challenge got lower losses, probably, but they get a higher test loss. Then it could be a classical case of overfitting. This can be the first thing. The second thing I can think of is the discrepancy between the objective used during training and the objective used during evaluation or testing. So take, for example, object detection. During training, we typically use smooth L1 for class localization and cross entropy or focal loss or some kind of sampler, so hard example mining plus cross entropy. This is what you do in training, but in testing, you're using AP. And we know that AP is not sensitive to localization. It's not looking at localization and classification in a unified manner, and so on. So the objectives used in training and testing are, first of all, different. they are correlated, of course, but they are different. And in a recent work of ours, which is not published yet, we used the LRP metric, localization recall precision, during both training and testing, and it makes a huge difference. When your objective during training is the same with your objective in your evaluation, then it makes a big difference. Then now these are unified and you are not optimizing different things and evaluating different things. I think this use of metric, the discrepancy between the evaluation metric and the training objective might be the culprit here.
Anyone else have thoughts to add on that?
I guess that connects to what Larry said this morning, that I think the organizers of COCO think that it's basically reached the saturation point where there's no more progress on it. And apparently the submission numbers also went down, so it looks like the community also maybe switches to different challenges, probably for similar reasons. And it's kind of interesting to see these how these data sets that have been around for many years, how their initial creators then start talking about having to retire them, right? So I think Andreas Geiger is saying the same thing, has been saying the same thing for 2 years now about the Kitty data set for similar reasons. And then it's about creating new data sets that pushing the field forward again. Are there any thoughts maybe from panelists or from the audience on are there any data sets missing that we should that the community should invest efforts in creating something that we don't have at the moment? Or do we just have enough data sets on? Is everybody saturated with challenges and benchmark tasks to work on?
Today, there definitely feels like there's a glut of them coming out at present, because I think particularly once Turk became very heavily usable, people were able to not have to go through as many personal man hours to be able to create their data sets, and they're able to, and using the insights gained from all the other challenges, we've been able to see quite the boom of them. But I don't know whether or not there's always the right data set for the right challenge for the right particular problem that people are trying to answer. Though I do not know all problems, therefore I do not know all data sets that need to exist for them. So.
Maybe referring also to some other papers, maybe we need a data set, like if I again think of autonomous driving, and a data set that tries to give priorities to targets and objects. Priorities in terms of, you cannot miss these, and like the importance, as we've seen before, right? The importance of each ground truth object is not the same, and maybe we might want to like, this is really task dependent, but we might say yes, but it's not so, it's basically the evaluation metric, I would say, in the end, but you want to stress that not objects are the same. And so in COCO, for example, these hundreds of books on the shelves, right? We do have in COCO these. I mean, looking at images in COCO and try to see to do some qualitative evaluation, just realize that you realize that there are like crowds of people in the background, and some are annotated or just and you do have strong feeling, okay, these objects are definitely less important in a real world application than objects that are near the foreground, that are closer to the potential car or robot or whatever. So maybe a data set that try to underline this, and with the challenge of that really penalizes errors that have an impact and doesn't really care about those situations that are also ambiguous for annotators, right? It's maybe where we have more errors, right? The very small objects, very far objects. Maybe there you can be less, you can punish less. mAP detector. That might be a way.
Yeah, I just want to mention that's like very similar actually to our workshop submission.
Yeah, that's I know. I just
has
wanted
like
to
a
point
nice
out
lab.
yeah.
Yeah. Yeah, I definitely agree with what you're saying. So one option is like kind of to hard code things like we know we should care about cars that are like directly in front of us, or that like have their like are about to brake, or like are about to cross our path that we're about to travel through. But I like if you start like one thing I did at have tried is like I've tried hard coding those kinds of things, and those are definitely useful, right? Because you find instances where your object detector is like doing something very wrong, and it's like very interpretable, like why you found that this situation was wrong. Like, but there are always going to be cases like where the object detector actually did something terribly wrong, but like your heuristics for like what was especially wrong didn't quite capture the driving task. Yeah, so I think that's hard. But yeah, I think a combination of like handwriting things that you know your detector should be doing well, to figure out where it's doing things incorrectly, and also maybe more abstract metrics like the one that we proposed in our workshop paper. I think a combination can help a lot. And I also wanted to mention that I'm like very excited about panoptic segmentation as like another kind of task that people are working on, and I actually wonder also if that's a reason that that the COCO benchmark is like falling out of favor also, because panoptic segmentation is just like a sexier task maybe, because like you get these per pixel labels. You're not doing regression, but it also has like instances. Yeah, so I actually wonder if you took your best panoptic segmentation network and then just created boxes from the instances. I wonder how that performs on COCO. I don't know if people have done that as a baseline.
Emre, I had one question for you that I was just interested in when listening to your talk. So you make a big point about the fact that LRP is definitely defined as a metric, unlike AP, and the principle behind what makes a metric and what doesn't. What I was wondering whether you could possibly go into a bit more as to what problems come from the fact that AP is not a metric, and what, whenever someone is creating an evaluation measure, whether they should ensure that it is a metric and what might be hidden under the surface if they haven't made sure about that.
Okay, yeah, thank you. So metricity provides us consistent distance functions, but it's not really a must, right? AP is not a metric. AP cannot be a metric, but 1 minus AP is not a metric either. And we used it for decades, right? So, so metricity is not really required in evaluation. The potential, its benefits. So the first paper of our paper, Kemal is our PhD student. He's very excited about LRP being a metric. I'm not that excited as him, but well, I cannot tell you any concrete benefits of being a metric. We made a comparison in an upcoming paper with the panoptic quality, which is the quality measure proposed specifically to evaluate panoptic segmentation. And panoptic quality, we show that it's just a special case of LRP. And there's a very little difference. And LRT was proposed earlier. And LRP being a metric gives us a smooth performance curve when you change for example, the mask of the object gradually, where PQ makes a big jump when the intersection over union threshold is above the threshold, but LRP behaves more smoothly there. And I think it's a good thing when you're optimizing it as a using it as a training loss. Yeah, that's all I can say, I think.
No, thank you. It was nothing. It was just one of those things that was brought up in that original paper and in your talk that I kept on going. Am I missing something that's like dreadfully important that could be like hiding under the surface of other evaluation measures if they haven't been formally defined as metrics? So thank you.
Yeah.
In another very sort of paper-specific question for Marco, I really did enjoy the problem being examined. I had not realized quite how fragile things had been to sort of translations before. I in that first Leaf paper that I talked about, I also noticed something, but only after very severe translations occurred. And even then, people told me that I was being ridiculous. That of course, a neural network can cope with that. But one thing I was interested in your paper is that you were very much dealing with trying to sort of the huge problem that I kept on seeing in your paper was the problem you were trying to overcome, which was just that the AP ranking situation. And what you were talking about before, how just a small change and then suddenly the entire ranking of everything has drastically changed. Have you considered potentially since then looking at other evaluation measures such as the sort of tuning around horn, things that are of the type of PDQ where you can have that sort of very much an image-wise analysis where it doesn't really affect how everything else works in the evaluation procedure? Would that be a benefit to you at all, or is that just cutting down on some time?
Yeah. So we investigated. So why did we go for AP at the end? Because we thought it was the most convincing message, because that's why you evaluate your detector. That's how you evaluate your detector, right? So that even if we are here arguing that you should not, I mean, it's still like the way. And so that was why we said, okay, let's first motivate how severe the problem is just by saying, yeah, you just shift one pixel and your state of the art is not state of the art, or your whatever becomes state of the art. So what is state of the art then? But we did evaluate other things. So one possible thing is to, one possible way is to measure per ground truth. So you can just take each ground truth object and track how it is, with which confidence and with which IUU it is found when you move things around. So then it becomes per object, not even per image, and you get very nice visualizations. We didn't put that in the paper because they were kind of out of scope, maybe a bit. But if you track the confidence to which some object is found, and you shift the image, let's say 20 pixel horizontally, 20 pixel vertically, you get a 20 by 20 image with the score of that object, and you can see very beautiful patterns, I would say beautiful, that are like every 4 pixel or every 8 pixel, every 16 pixel, and this is really the downsampling of the network or the anchor box grid. So this is like another way that doesn't suffer from the problem of AP, but then it was really, for us, it was really an incomplete way of measuring shifting variance, because then you miss all the false positives. You don't consider the false positives. You don't consider localization accuracy. So yeah, we can definitely investigate other metrics, PDQ, and we tried also AP per image. So you can actually compute the AP per image, right? It kind of loses a bit its sense.
As soon as you're down to small scales, everything gets muddled and yeah.
You can maybe just by ignoring the class, just by ranking every object, not separating them per class, because otherwise they basically are ranking it just one instance. And that also was a way, but then in the end you optimize for a different thing than your final metric, and so you end up with a suboptimal shift selection. So yeah, this is what we investigated, but yeah, I agree, we can go farther in that.
Oh, cool. It was definitely though just fascinating seeing the fragility of systems to just a single pixel. That was fun.
Yeah, we saw it in our data first. Like we read that paper about making CNNs shift invariant again, and we just said, okay, let's just try our detector to see if it is shift invariant. And we were shocked. Whatever, if you crop the image, but the cropping, we were against cropping because you remove context, but just by shifting it in a big black background image, you just see, okay, what's happening here? I'm missing objects that I shouldn't miss. And this translated from our own dataset, internal dataset, to COCO. And that's why it went.
Cool. I'll throw open to the panel. Does anyone have any questions they would like to ask anyone else based on what they've seen in their talks, etc.?
I have a question regarding the detector ensembles, because by reading the papers, I think I didn't see any paper that tries to do the following. So is it possible to take a detector and just take a snapshot from different iterations? Let's say the last 20,000 iteration, you get several snapshots. And so you get basically several different models. So how do these models work as an ensemble? Like maybe for probabilistic object detection. Maybe I missed it if it's in one of the papers, but do you have experience? Have you tried this? So like, is the model difference between different iterations high enough to get a nice estimate of uncertainty?
I think normally you could do multiple things. You could start, or you could train for multiple initializations. That's sort of then it converges to multiple local minima, and then you have multiple ensembles. That's sort of the deep ensembles approach, right? You could just average the results of those together, which then would give you a distribution over boxes and over these label distributions. I think another idea is that's called stochastic weight averaging, that you start from from one initialization, then you learn for a little bit, and you decrease your learning rate, but then instead of decreasing it to the point until you converge, you keep the learning rate constant at still like a pretty high rate, which then means your optimizer is jumping quite far along sort of in one of those local minima, but it's not actually converging to one. And then you can do the similar thing. You could just average those, or you could actually estimate the distribution over weights by maybe just a low rank diagonal Gaussian covariance matrix, and then sample from that, and then actually get in a nice Bayesian way a posterior over the weights, and then you get a full distribution over the predictions. So there are a few ideas like this around, which would actually be interesting to see how that performs in terms of PDQ, and if that performs better on PDQ or open set conditions than what we've seen this year. But I think the winning approach this year was using 3 architectures that were different, and they were trained to convergence, and then they were sort of merged together with a scheme where the best performing one could sort of get all its detections in, and then it was merged with the second best, and then the remaining detections from the second best would then try to merge with some from the third best, and then that's how the author built that up. That was the best entry for this year. I think there's still a lot of interesting things to try in terms of Bayesian deep learning for object detection that we would hope to see in the future. So if some of you in the audience are motivated to try these things, David, we have maybe you can say a few more words about that, but we have a constant, an ongoing leaderboard where you can submit to, and you can see the results, how you perform to this year's challenge entries.
Yeah, no. So we've got for the probabilistic object detection challenge, there's the main sort of test server, which is currently closed for ECCV. But we have a validation set where you can test your methods, and you can even test that offline in your own labs. But we also have a test dev set where you will not have access to that test data, but can still see how good your probabilistic object detectors perform on a previously unseen data set. So of very similar size and scope to the main test set of the challenge. So yes, definitely if people are interested in probabilistic object detection, I would encourage them to use that as a resource. It gives you all the breakdowns of PDQs to the different aspects of probabilistic object detection that you might be doing well at, doing poorly at. And yeah, no, I definitely encourage it, and hopefully we'll be able to run another official challenge sometime next year. I'm still deciding exactly how. And if you are interested in robotic vision challenges in general, things that might have good real-world applications, at our website of roboticvisionchallenge.org, you can find information for first of all, for this workshop, you'll be able to go to there and find links to all of the paper pages for all of the presentations that we've got associated with this workshop, but also information on our probabilistic object detection challenge, PDQ, the evaluation measure for it, and our new scene understanding challenge, which has embodied agents in simulated environments, trying to map out objects within a 3D space. So all information for all those challenges is there on the website. Thank you, Niko, for posting that into the chat. All right. Are there any other questions from the panelists? If not, we may call this and finish early, as we seem to have.
Yeah, I have another question actually. Yeah, I'm actually just curious what you guys thought about like this end-to-end object detection paper from Facebook that came out. If you guys had any reactions to that.
Which one?
I have to admit, I have not seen it.
Okay, yeah. So this is a paper that I guess their main idea is to try to get around this, like the NMS post-processing, and their approach is basically to have something that looks like a transformer model, which given like a C by H by W representation of the image, it kind of attends to different parts of the image and outputs a bounding box, basically. And they have a bunch of different heads, and each head basically outputs a detection, along with like a confidence score about if like there's actually an object there. Yeah, I thought this was interesting. So number one, like this violates spatial or like shift equivariance, right? Because you have a model which is globally like looking at coordinates, and the transformer needs coordinate location representations, because otherwise it's just unordered. But second, like in return, like you maybe don't have to have as many hyperparameters in your like post-processing. Yeah, so I thought it was interesting, but yeah, I was just curious. If you guys didn't see it, I think it's worth checking out.
Yeah, so I would be really interested in testing it for shift invariance, shift equivariance, because I mean, they are predicting a set, and I think there's also another paper about set predictions, because like objects in an image, I wouldn't say they are much like ordered. Like we order them by having anchor boxes and doing matching with them and just find out the matching there. But in this paper, if I just remember, I read this Detectors paper, but this was, yeah, they really proposed this as a set prediction task. So it might be very interesting because they have the positional encoding, but actually, as you say, right, really encode global location, and they just give the global location to the network, so it can't be it's not meant to be shifted equivariant, but but the set prediction is more towards the shift invariant idea for me, because whatever the object is, you don't want to change the matching between this object and a certain anchor when the object moves through the image. So it might be non-trivial, the effect of this on the shift equivariance properties. Yeah, definitely a new paradigm. They didn't get the ball numbers in the end, like not that much, right, in the end, but that's, we say maybe that's not what we care about. This is a completely different approach, so that's already great.
Yeah, that paper is, I think, very interesting. It's a different approach than the typical paradigm. I think they have two important things that they bring on the table. First is the set prediction and this positional encoding, which gets rid of the NMS part at the end, which is very important. That's a good, I think, improvement. And the other thing is they use transformers, sorry, so that they put long-range interactions into detection. So in transformers, you know, this spatial attention thing, a feature in this location affects the features in other locations, like in non-local neural networks also. So long-range interactions and this set prediction are the main things. And connected with that, I'd like to mention another paper at this ECCV, which is from our group. That's why I know the paper. It's called HuffNet. It generalizes this. It uses this generalized Huff voting idea to detect objects, and it's a nice way of encoding long-range interactions. So, for example, a typical object detector, when detecting a computer mouse, for example, uses the local features at near the mouse or at the mouse, right? But mouse typically co-appear with a monitor, a keyboard, or a table, and those long-range interactions, so the other objects vote for the mouse detection, and we show that it's extremely, especially beneficial for small object detection. So long-range interactions help as a context for the detection of small objects.
I have a question regarding this. Do you think this long-range interaction might lead to kind of hallucinated predictions, like if you see a crowd of humans and then something, you would predict that as a human because it's surrounded by other objects that kind of like, motivate the presence of an object there, but that maybe that object isn't there. So have you noticed this? Can it also
That's a very
be a problem?
good question. We thought of this, but we didn't do experiments on it. So, for example, you can occlude an object and then just run HuffNet and see if it detects, if it predicts that object there. So we don't know the answer, but it has the local features. It uses local features and also the voting features. So hallucination effect, when the context is very strong, might be there. But since it also uses local features, it might not be there. So I think it's an experimental question. We don't know.
Yeah, I think the case is in Coco, the classic case, right? The cup held by a hand. So there has to be a hand, right? Because there's a cup. Or in Coco, the skis, you have snow, you have a human. Yeah, it has to be skis or a snowboard there, right? So if you occlude them, I would be very interested to see if the detector is.
Okay.
Thank you.
All right, did anyone on the panel have any other questions? We haven't gotten anything more from our audience at this point. No? All right, in which case I'd like to very much thank all of the panelists for joining us today for this conversation on the often overlooked topic of object detection evaluation and just evaluation measures in general. This has been great for me. I've thoroughly enjoyed both of the interactive sessions. It's been great hearing the different perspectives from people talking about the evaluation measures themselves to the entire paradigm of detector and data set and how they influence each other. So this has been really great. I would highly recommend anyone in the audience to definitely check out the various presentations that we've got for this workshop. They've been very insightful and very interesting. And hopefully they will inspire you to start thinking about how you evaluate your object detectors just a little bit differently. So thank you everyone very much for joining me. Cheers.
Thank you.
Thank you.